What we want to do now is take a look at the energy transformations that take place inside an electric circuit. Here is your basic electric circuit. It's got a battery hooked up to a resistance. What exactly is a resistance? Well, a resistance is something that changes electrical potential energy to heat energy, like the filament inside an incandescent light bulb or a stove element. And if you want to see the gory details of what's happening on an atomic level when electrons go through a resistance, here we are. So the electrical symbol for resistance is a jagged bolt of lightning thingy like this. And what's happening to electrons as they go through a resistance on an atomic level? Well, the atoms in a resistance, they kind of look like the atoms in an insulator. They are jumbled around all over the place at random. And the electrons, they don't just zip through as if nothing is there. The electrons, they really struggle to get through a resistance, and as they go through a resistance, they are ping-ponging back and forth from one atom to the next. And whenever they run into an atom, well, they set that atom vibrating. And you can imagine, when one electron goes all the way through a resistance, it's going to set a whole bunch of electrons vibrating back and forth. And that's what heat energy is, the vibration of atoms. So now you can see exactly what's going on, how electrical potential energy gets changed into the motion of atoms, which is basically heat energy. Okay. Back to our main circuit here. So remember over here we have a battery, just like any source, it's got a negative terminal with a bunch of negative charges and a positive terminal with a bunch of positive charges, and you can see that the negative terminal is going to push the electrons in this direction and the positive terminal is going to pull the electrons in the same direction. And when these electrons, when they hit the resistance over here, what's happening to them? Well, remember, they have to fight their way through the resistance. So you get kind of a traffic jam over here where the resistance is. All the electrons, they kind of pile up there, waiting for the electrons ahead of them to fight their way through. What happens over here? Well, the electrons in this region of wire, they got a free ride back to the battery, so they're going to vacate this region pretty quickly, but the electrons coming in to replace them, they're being slowed up by the resistance, so in this region you get a bunch of lonely protons. Their electrons, they zip off to the battery, and you got a bunch of laggard electrons trying to fight their way through the resistance to replace them. So over here you have a buildup of lonely protons. So keep that in mind. We have a charge imbalance across the battery, right? Bunch of positives here, bunch of negatives here, a charge imbalance or a potential difference across the battery, and the same thing across the resistance. We have a charge imbalance, a bunch of positives here, a bunch of negatives here. That means we have a potential difference across the resistance. Okay, now before we go any further, we're actually going to talk about a mass moving around in a gravitational field, because a mass moving around in a gravitational field is very similar to electrons flowing around an electric circuit. Okay? So here's a mass, and I'm going to move it around a gravitational field. I'm going to move it around, nothing special, just like this. Okay, now what's going on there as far as energy is concerned? Well, when I pick the mass up, I'm converting chemical energy in my muscles. I'm doing work on it, and I'm converting chemical energy in my muscles to gravitational potential energy of the mass. And as I move the mass across, okay, and it's pretty easy to move it across friction and air resistance are pretty much negligible, so it kind of gets a free ride across, doesn't take any work to move it across, and as I move it across, its gravitational potential energy doesn't change. And when I do this, well, the gravitational potential energy, it decreases, it gets changed to kinetic energy. And then of course, as I move it across like this, if friction and air resistance are pretty much negligible, it gets almost a free ride, doesn't take very much work at all to move it across. The gravitational potential energy isn't changing, and the cycle repeats. Increase in gravitational potential energy, no change in gravitational potential energy, decrease in gravitational potential energy, no change in gravitational potential energy. Okay? And the cycle repeats. Increase, no change, decrease, no change. It is the exact same thing with an electric circuit, except instead of talking about gravitational energy, or pardon me, gravitational potential energy, now you're talking about electrical potential energy. So let's follow the path of one lousy little electron that, let's say, is going to start off right there. Okay, so we have an electron right there at the positive terminal of the battery, and it wants to go, or it's going to go in this direction around the circuit. Now, if it's sitting there, remember, these positives are pulling it down, these negatives are pushing it down. That electron does not want to go on its own from here to here. It's kind of like the mass. To pick the mass up, I got to do work on it. Okay? Well, to get that electron from here to here, the battery has to do work on it. The battery converts chemical energy to electrical potential energy. Okay? Just like I converted chemical energy to gravitational potential energy, well, the battery converts chemical energy to electrical potential energy. And once the electron is there, it's in amongst all these negatives. Well, these negatives, they're ready to like cast it off into the universe and let it do great things. Like once the electron is there, it's kind of like this mass. Once I got it over the table, okay, these electrons, they have a lot of electrical potential energy. So through a battery, we call that a potential increase, because the electrical potential energy of the electron is increased. And then of course, as the electron moves from here to here, it's going through a conductor. It's like a free ride, doesn't take any work. There's no change in potential. You notice a bunch of negatives here, a bunch of negatives here. That isn't a charge imbalance. So there's no potential difference between here and here. So the electron in this region, it has a lot of electrical potential energy, and it doesn't change all the way from here to here. It keeps that whole bunch of electrical potential energy. Once the electron gets to here, now that's kind of like the mass falling down. The gravitational potential energy gets changed to kinetic energy. Well, look here. Once the electron gets to here, these electrons, they're pushing it that way. These positives, they're pulling it that way. So that electron, it'll go from here to here on its own, but as it does, remember, it's running into all the atoms inside the resistance, and it is changing its electrical potential energy into heat energy. So when the electron gets to here, well, it's kind of like the mass on the table. No gravitational potential energy. Once the electron gets to here, it doesn't have any electrical potential energy left, and it just kind of glides along because it doesn't take any work. It's really easy to move through a conductor, and it glides along back to here and starts the process over. So through the resistance, you have what's called a potential decrease, because the electrical potential energy of the electron gets decreased. Okay? And that's what I want you to realize from this diagram. If you're an electron, you're going around a circuit, potential increase, no change of potential, potential decrease, no change of potential, potential increase, and so on and so forth. Last thing we want to talk about is Kirchhoff's second law. This is what we really want you to remember about circuits like this. And it's pretty easy. The potential increase through the source is going to equal the potential decrease through the load. It's no different than moving that mass around, right? The potential increase on this side is going to equal the potential decrease on that side. Except with a mass, you're talking about gravitational potential energy, and of course with a circuit, you're talking about electrical potential energy. But same idea. The increase through the source is going to equal the decrease through the load. And if you really want to be picky about it, if you're talking about this circuit here, the potential energy, or pardon me, the potential increase through the source is going to equal the potential decrease through the load, okay, plus the potential decrease through the conductor. When electrons, when they go through a conductor, they do of course run into the odd atom, cause it to vibrate a little. That means when electrons go through a conductor, they are producing a little bit of heat. They are losing a little bit of electrical potential energy. So there is a small amount of potential decrease through a conductor. But the key word there is small. So we usually ignore that. As far as an assignment is concerned, you'll notice at the end of the PDF, there's a little blurb about different types of sources that you should read. And then there's some questions attached to the PDF that you should try. Don't bother doing them all. Make sure you do questions 1, 2, and 5. That should be enough. We will see you later.